the logistics out of the way. So again, welcome to E5310 analog electronic circuits, and today is the introductory class. I will go over what we are going to cover in this course. The outline of this course is as follows. We will first take a brief breather and a refresher on linear and nonlinear circuits. And more importantly, understand the notion of incremental operation. Then we will learn about how to make amplifiers, and we will see that nonlinearity is fundamental to making small signal amplification, and we will see how the MOSFET comes about. Then, based on our knowledge of active devices, an example being the MOSFET, we will then look at making the 4 basic control sources: the current controlled voltage source, the voltage controlled voltage source, the voltage controlled current source, and the current controlled current source using transistors. And we will follow that up with making multi-stage amplifiers. And finally, look at the operational amplifier. In that process, we will learn about frequency compensation, and how to stabilize a potentially unstable system. Okay. So, a lot of this material is most likely familiar to you because you have seen this in earlier courses, but in any case we will start afresh and go slowly, and feel free to stop me at any time for questions. How many of you are MTech students here? 22 batch? Okay, all right. So, very good. So, let us get started. Okay. So, for large parts of your prior curriculum in your engineering classes, you spent a lot of time learning about linear circuits and systems, okay, and not merely in your circuits classes, but also in your courses on communication and things like that, and control for that matter, where you have spent at least 4 or 5 courses learning about linear systems. When you learn signals and systems, you are learning about Fourier transforms and Laplace transforms, which are basically applicable to the analysis of linear systems. When you go to linear integrated circuits or linear networks or linear circuit theory, again you spent a lot of time learning about how to apply Laplace transforms to the analysis of linear circuits, correct? Initial conditions, all this fun stuff. Then when you went to communication, you basically spent again a lot of time learning about Fourier transforms and what happens when a signal goes through a linear system and convolution and all this fun stuff. Okay. And finally, in control, again you have learnt about how to apply Laplace transforms to the analysis and analysis of feedback systems, where every block is linear, correct. Okay. And I hope all of you appreciate the fact that the only a linear system is perhaps the only one which is amenable to the analysis using transform techniques, correct. And so obviously therefore the bottom line is that you spent a lot of time learning about linear systems and tools to analyze linear systems, namely the Laplace and the Fourier transform, correct. But unfortunately, you know that the world is nonlinear. There is nothing called a perfectly linear element. It's only degrees of nonlinearity that vary, and therefore it appears as if you spent all your time learning about systems that are linear and time invariant, correct. But unfortunately, the real world is neither linear nor time invariant. At least time variance apart, to begin with, it is not linear. Okay, and if a system is not linear, none of the tools that you use, right. So for example, the Laplace transform. Why do you think you spend so? What is so great about the Laplace transform, and why is it so useful? Why is it useful? So, the key attribute of a linear system is that if you have a system which is say, and for simplicity, let us assume the system is also time invariant. So, this is linear and time invariant, then if you apply an arbitrary input x of t to the system, the output is y of t, okay. And you can always think of y of t. So, let us say this is some x of t, and if you think of the input as a series of thin slivers like this, for example, here is one. So, you can break this up into a bunch of thin slivers like that, and each sliver can be thought of as, you can think of it as a small impulse, and if you know the response of the output response of the system to an impulse, then because the system is linear, you know its response to a scaled impulse, correct. And because the system is time invariant, if you delay the input, the output is also going to get delayed by the same amount. So, so basically, if you know the response of the system to an impulse, the output is simply seen to be given by, how will you find the output? It is simply the convolution of this is provided it is LTI, but this even in an LTI system there is an important, the initial conditions must be 0. So, fine. So what? So why are transform techniques so useful therefore? So the key point is that in the transform domain, y of s is simply x of s times h of s. In other words, in the transform domain, convolution becomes multiplication. You cannot do this since this is not valid. So since this is not valid for a nonlinear system, the transform domain what do you call tools become inapplicable, and therefore, the analysis of nonlinear systems and circuits is fundamentally more difficult to do than a linear system. Okay. And as a case in point, let me take an example. So, this is R1, this is R2, this is Vi. What is that output? It is Vi times R2 by R1 plus R2, right. It is so obvious that you may think that the circuit is all, I mean, this question is almost insulting, all right. Now, what is the simplest? Let us now, this is perhaps the simplest linear circuit that I can think of. There is no memory, there are two components, right. So, if you want to think of a simplest nonlinear circuit, what do you think you will do? You replace one of these elements by some nonlinear element that you know. So, what is the simplest nonlinear element that you know? The diode. Okay. So, the diode let us say is I do not know, I mean, I just put it there. So, this is R2 and this is Vi. What is the output voltage? How would we figure this out? What conditions?
If Vi is greater than 0.
No, by the way, what is the equation for what is the IV relationship for a diode? This is I, this is let us call this Vd, and this is Id. How is the current related to the voltage? Id is some Is exponential Vd over Vt minus 1, okay. And what is Vt? Kt over Q, where K is the Boltzmann's constant, T is absolute temperature and Q is charge on an electron, and this is approximately 25.8 millivolts at room temperature, but for our purposes we will simply use a round number 25 millivolts, okay. And if you are not happy with this, then I am going to say, well, we cool down the room until the Vt is equal to 25 millivolts, okay. All right. Now, the question is, what is, how do we figure out what V naught is? This is the IV characteristic of the nonlinear element. So, what do we do? How do we figure out what the output voltage here in this circuit is? Pardon?
We can apply KVL and
that is all, right. As electrical engineers, right, the only thing we know is to apply KCL and KVL, all right, that is what we are going to do. So, we do not know anything. So, we are going to say, well, this current in the loop is unknown, that is some I, okay, and write Kirchhoff's voltage law, that is KVL. So, Vi is nothing but the voltage drop across the diode plus the voltage drop across the resistor. So, that is basically Vd plus I times R2. Does that make sense? Okay. Now, Vd unfortunately is not explicitly known in terms of Id, correct. Vd is a nonlinear function of Id, and so what comment can we make if Id is given by this equation? What comment can we make about how is Id related to, or how is Vd related to Id? Well, couple of observations first. It always makes sense to draw a picture when you see an equation. So, if I plot Vd on the x axis and Id on the y axis, how does that picture look? for Vd which is large and negative, so Vd being large and negative basically means what? Mod Vd is, by the way, what is the meaning of large? When I say Vd is large, what does it mean?
Means by which function we are comparing it. Means here we are comparing with Vt.
Correct. So, very good. So, basically this please note that this notion of large, small, thin, fat, all these are relative terms, right. It does not mean that 25 millivolts is a small value. Of course, it is small when compared to 200 volts, but it is very small when compared to 2 microvolts. Okay. So, similarly when you say large Vd, it must be in comparison with something else, and that something else depends on context, correct. And in this context, what comment can we make about Vd? When you say a large negative Vd, what does it mean? It must be with respect to Vt. So, therefore, if for Vd absolute value of Vd much larger than Vt, what comment can we make about the diode current? You can ignore which part? You can ignore the exponential term, and therefore, Id becomes nothing but minus Is. Okay. So, you draw something like this, and if you want to see Is on the same picture as the for when Vd is greater than 0, the only way to do that is to observe that this must be a different scale. Okay. If you go and pick up a diode in the market, I mean typically these diodes will have the reverse saturation currents of the order of maybe a few hundred picoamps. Okay. And so when Vd equals 0, what is the current? 0. Okay. And when Vd is much greater than Vt, what comment can you make? It is an exponential function. Okay. And Id is approximately Is e to the Vd over Vt. Correct. So, first things first, staring at this picture of the circuit, can we figure out whether the Vd is greater than 0 or Vd is less than 0? If Vi is positive, do you think Vd is greater than 0 or less than 0? It is greater than 0, that is apparent, I think, right. So, so then which part of the equation will you use? Use the exponential part. So, assuming Vi is greater than 0, it follows that I is exponential Vd over Vt, where we neglect the negative 1, and therefore, what comment can you make about Vd? Vt natural logarithm of, I forgot to put an Is here. So, I is nothing but Is exponential Vd by Vt. So, this is Vt ln I over Is. That makes sense, people? Okay. So, now therefore, you just plop this into our equation, Kirchhoff's voltage law equation here. So, Vi is nothing but Vt ln I over Is plus I times R2. So, what is the known, what are all the known quantities here and what are unknown? Which all are known? Vi is known or no? This is the applied voltage, we know that. What about Vt? Known. Is? It's known because we know the property of the diode. I is unknown. What about R2? No. Okay. So, clearly this is one nonlinear equation in one unknown. Okay. Unfortunately, this is a difficult nonlinear equation to solve. This is a transcendental equation, and therefore, how do we go about, what do you propose that we do to go and find I? Yeah. So, I mean, you can pick your favorite numerical algorithm to find the solution, right. So, in other words, finding the solution is not easy. Analytically, but then we say, well, the solution to this is that you find it numerically, given Vi, Vt, Is and R2, you go and you can go and go to your favorite mathematical package, Octave or MATLAB or whatever, plop these numbers in, and the package will solve the equation for you, and you will basically get the current I. All right. And by the way, this region of operation of the diode, what is this region of operation called? It is called forward bias. And this region is called reverse bias. So, to summarize our discussion so far, even the simplest nonlinear network that one can think of, where you have taken that trivial R1 R2 network and replaced one of the resistors with the simplest nonlinear element that we know, namely the diode, already we can see that finding even something as simple as the loop current, right, which we did by inspection when we looked at that R1 R2 network, has already become quite complicated, and we need to resort to the use of MATLAB to basically, or some kind of similar numerical package to go and actually find the current I. Okay. Now, let us say you have gone and done all this hard work, and so you have gone and done all this hard work, and you gotten, once we find I, how will we find VO? I times R2, correct. So, let us say we have gone and found this network, solved this network completely. Now, somebody comes and tells you, okay, well, I am going to change the input voltage by a small amount, okay, and now can you tell me what the output voltage?